So last session we started talking about stacking up different or multiple layer of perceptron in order to present more sophisticated representation of classifications for those type of data that they're not linearly separable, and we carry on with the notation that what if instead of using a perceptron as a classifier, what if we use a nonlinear classifier such as sigmoid? And so we went on to define a very preliminary neural network. I believe it was a 2-layer with one hidden layer in the middle. So we see one more example here now today, and then we carry on with a more formal definition of neural networks today, and how the feed-forward path actually works. Then next session we're going to start talking about how the backward path, or what is well known as backprop, works in neural networks. All right, so in this example, suppose we have two hypotheses, H1 and H2. So that was for the H1 case, and this is the H2 case, right? So we are interested in classifying two different data. So the first one goes x1 plus x2 equal to 1. The second one is x1 minus x2 equal to 2. So if we go on into stack these two together to represent an OR function, so we're going to have these two stacked together like this. In this case, they're going to represent the OR. And as you see, this actually represents that if either of them was +1, the classification results in a +1 or plus. And if both of them were -1, we're going to end up being like here. And that represents the other class that we were trying to classify. On the other hand, we talked about the other function we could build with a simple multi-layer perceptron, which was AND. In the case of AND, you see that if both of our hypotheses are defining the class of pluses, so we only be able to classify the plus there, and then the rest of the cases, because the AND function returns 1 only if both of the H1 and H2 were 1. So in this case, we could represent a nonlinear data set such as this. So using these two, we can optimize, and we can represent much more complex representations. The way we add these ANDs and ORs together, and we're going to see some examples today. Okay. All right, now let's see by combining AND and OR, how we're going to represent XOR function. So that was a 2 line here, our two H1 and H2. So on the case of XOR, we have to stack these two up. So in this case, we're going to have two hidden layers. The input comes from x0 is equal to 1, x1 and x2, and either of these are pointing are passing their weights, which are +1, and because of this line it was -2 and +2, towards the next layer, and this layer represents our edges. So basically we start from our input, represents our edges, and then combining edges multiple times in hidden units finally with an activation function we're going to have the output y. So this is a very high level representation of a neural network. So basically by feed forwarding, if you go from left to right, we're gonna call it feed forward or forward pass. Forward pass. So here we made our H1 and H2. Here was the combination of H1 and H2. One case positive, one case the negation. H1 negation H2. And then here's going to be the output. So as you see here, we are using a hard threshold as our activation function. So later on, they change this into a sigmoid function, and later on, they change it to a hyperbolic tangent. And nowadays, we have so many other variants, depending on the designer's choice. We see a couple of them actually more in the CNNs when we are talking about the convolutional neural networks. So designers have seen that by using different type of nonlinearity, they're able to soft threshold the weights in a better way so that the output accuracy is higher depending on the problem. Okay, so in this case, let me just get rid of this. Just get rid of this. So in this case, our output function was representing an XOR for us. So H1 negation of H2 plus H1 negation and H2. So this is normally known as disjunctions of conjunctions. So conjunctions could be an or any other binary classification that you can design, and then you can represent more complex things with the disjunction of those conjunctions. So in the 70s and 80s, they found that any decision region can be represented by a multi-layer perceptron. However, this theory wasn't proved up until 1989. So we're going to see the definition of the theory later on in this class. All right, any questions so far?
So the H1 layer also feeds into the next layer, right?
Yeah, I don't know. Disappeared somewhere. Yeah, it actually here. Also this one. This should be this as well. Okay, is it clear now? All right. So, one question would be why can't we have a good working with high performance and high accuracy neural network with a linear function, right? So what if we use a linear function instead of sigmoid? We use theta of s equal to s, which is a linear classifier, right? So instead of going this, instead of going a hard threshold or our sigmoid function, so this is hard, that was our sigmoid. Why not we go like this, a linear? So in that case, your output y would be the output of the function theta, which was a linear classifier of v0 plus the summation of j's from 1 to n, vj w, a vector of weights transpose of j multiplied by your inputs, right? And that was a linear function in x because this was linear as well, right? So I guess I have to close this back. Yeah. So it's better now. Okay. Because if you calculate the output of that, it would be V0 plus W transpose X, and we would call this WEFF, just to distinguish between our previous W's with this one. Thus, WEFF was the summation of Vj WJs, as we mentioned there up. And finally, as you know, this is, so if you use a linear function as your classifier in a neural network and you stack them up in multiple layers, actually it would become a logistic regression at the end. So we wouldn't be able to make, better prediction rather than a simple logistic regression. But with the neural network, we are able to represent more complex, nonlinear data sets. Okay. That was why a nonlinear activation is very important in neural networks, so we call them sometimes NNs. So if you want to define a very high level process of a sample neural network, so you first apply a nonlinear transformation as h of j is equal to theta of W transpose j multiplied by x's for j's from I to n. And then we have to apply a logistic regression for that. You see the difference now? Between an NN, between a neural network and a logistic regression. So as if we have a logistic regression, but before that, we have applied a nonlinear transformation. And that's one of the superiorities of neural networks with respect to a logistic regression. Okay. So there's another interesting question. How is it different? How is this approach actually the way we define neural network? How is it different than a nonlinear transformation approach that we saw before in this class when we wanted to have a quadratic transformation? If you recall, we're trying to use a nonlinear transformation. For instance, when you have actually remember previously if we had a data set like this where one class was aggregated in middle and the others were like on the outside. So that was not having a linear separability. So we applied a nonlinear transformation. Right? And we differentiated between the pluses and the minuses. So that was a nonlinear transformation. Or another type was you were playing with the other sort of transformation in order to transform your nonlinear data set to a linear one, or the one you could actually represent in a lower dimension. So how is it, does anyone know, or can anyone guess why is it different than a nonlinear transformation? Because anyways, we are using a nonlinearity in the middle of a neural network, right? So suppose you have your x's as input, and this z was a function such as that to transform your x's from x space to a new space of z, which represent, in a second order, it was representing as 1, x1, x2, x1, x2, and either of them square 2. And then we could say apply logistic regression, right? So that would be one approach. Why do you think is it different than a neural network? Any guesses? Yeah.
Is it because for each layer of the neural network we have a different set of weights?
Right? Exactly. Because neural networks are trying to find the right set of hypotheses depending on the weights for us. Thus, this nonlinearity, the output of that is not going to be fixed, right? But a nonlinear transformation, you start from a transformation and you change your data. Whereas a neural network, you start from data and find the nonlinearity, right? And that's the huge superiority. You come from data and fine tune and find the exact set of weights through the optimizations, through the feed forward and backward pass using a stochastic gradient descent or any other optimization. You find that a specific weight that was the output of the hypothesis. So for instance, this h of I, which was the output of theta W transpose x, it depends on the W's. And these are not fixed, right? You could, in many domains or in any problem, you're going to have different weights. And we learn this as a part of the model. That was why neural networks are much more powerful than a nonlinear transformation. Also, as I mentioned, we can optimize them through a stochastic gradient descent or any other type of optimizations that you can apply on their structure. All right, so let's see a more complex example here. So we have 3 lines. So the problem is we are trying to classify these pluses and minuses, these 2 classes of data, right? So we have defined 3 L's. So that represents 3 different hypotheses for us: L1, L2, and L3. So with these 3, we can see that we can classify these data into 6 regions, for which 3 of them are pluses and the other 3 are minuses, right? If you break down all these 3 hypotheses into their individual lines, so it was as if you have L1 working like this, your L2 like this, and your L3 working like this, right? So now, if you want to combine these 3 and represent that presentation that you see up, so for the cases that you want to classify only the pluses, so we're going to have 3 regions, right? 3 R's. So we have to define these 3 R's. So the first one, if you see, we're going to have to make an AND of the case that H1 represents minuses, which is this, and combine them and AND them actually with the case that H2 represents the pluses, which is this as well, and a case that H3 was going to represent the pluses this way, so it was this. Thus, making an AND of these 3 hypotheses, 3 simple perceptrons here in this case, negation of H1, H2, and H3 actually represent this region. We call it R1. And you see that simply by stacking up those 3 H's, H1, H2, negation of H3, and H1, negation of H2 and H3, we can represent these 2 as well. So now, after combining these 3 with the OR function, we're going to see that our Y, the true output, would be 1 if your X's included in R1 plus R2 and plus R3 as the OR case. So this is going to be translated as if you have 1 input layer here, and then on the second layer you implement your H1, H2, and H3 individually, and then on your third layer you make an AND, it represents the AND case of those 3 H's, and finally you apply OR, and then you can output that, right? You see how intuitive is it? That's why it's very popular. All right, now after using it for sort of a decade or so, they were trying to understand if they can extrapolate this approach and sort of generalize it for any type of smooth functions. So by a smooth function, I'm talking about those functions that have derivations and the derivation is continuous. So suppose, I'll wait for the next slide. So they wanted to make sure that this approach is good enough in order to extrapolate and generalize it for all the functions that you can have, that you could build actually with the smaller perceptrons or sigmoids or any other type of activation functions. And in 1989, a researcher called George Sibenko, actually this guy was an alumni of U of T as well. So he was having his bachelor's here in the 80s. So he came up with the theory and the proof of that, and it was well known from it was well known for the name of universal approximation theory. Okay. Okay, so I put the proof of the theorem there, and it was well known after by the name of universal approximation theory. So it basically says that a three-layer neural network with sufficiently many hidden units in each layer can actually approximate any smooth decision boundary. So I underscore two different points of this theorem, which is approximation first, and then any smooth decision boundary. So this actually says that if you have a three-layer neural network, such as that, one input layer and two hidden layers, and with sufficiently high number of nodes, which are these are your nodes. So if you think about these nodes, they're actually representing the output of your features, right? So your input could be your features, and depending on how you expand your features in the second and third layer, you have different number of nodes. So in the case of a fully connected layer, you have to connect all the nodes with their previous layers and their succeeding layers. In other cases, in like CNNs or in convolutions, you're going to treat them differently. But say as a general case, a sample three-layer neural network can approximate any smooth decision boundary. So by smooth function, we are talking about those functions that their derivation is continuous. Like this function is smooth, right? However, this function is not smooth. Like this function, this is not smooth because its derivation in higher order is not continuous. Yet there are a bunch of properties involved with that. You can check if you were interested. But this was a very important breakthrough that people understood that they can optimize this process and they can represent the classification of any smooth function by a very good approximation depending on the type they design their network and by the type they optimize it and use their hyperparameter. They can approximate by a good extent. So actually, in his proof, he was talking about a sigmoid function, such as that. We have other proofs for other activation functions as well, but that was actually the first one that propose this proof. Okay, so now we're going to see. Let's just
So, what does it mean by sufficiently many?
Sufficiently many is like.
Like, is there like an exact number, or is it different per?
So it's a very general definition. So sufficiently many nodes is like how well accurate how well actually you want your prediction accuracy to be, right? So sometimes by having more nodes here, you're actually hurting your accuracy because it's an approximation function. So you have to just people for many years actually they have been doing trial and errors to experiment with like different hyperparameters, different optimizations, how they're going to play around with the design to come up with a better solution, right? Because in every level, you're representing nonlinearity. Because at the end, each of the layers are having their own activation function and their weights, and they're going to pass through the next layer. So this makes the optimization space very, very big. And that's why in general we call it like designer's choice. Okay. All right. So let's talk about some notations because you're gonna need them in order to define the forward pass. And later on next week we're gonna use them a lot in order to define our backward pass or back prop. So we call the input layer the first L, which was 0. The hidden layers, we call them by small l, which are starting from 1 up to the capital L, which was the output layer. So these three are representing our layers. Let me just close this again. Okay, so we're going to define Wi and j of L as the weight connecting node I in layer L-1, which was the previous layer, to node J in layer L, which is the current layer. Also, we define D of L as a number of nodes in that layer L, excluding the biases. So for now we are excluding the biases because each node has its own bias, right? A number of nodes could be from 0 to and this number of L's could be from 0 to L, right? Okay. All right. So that's going to be a sample representation of our notation. So we start from the first layer, or if you assume you're in the middle of your neural network, so it's going to be layer L-1, your previous layer, and this is your current layer. So your x's are coming from 1, x, x1, L-1, x2, L-1, up to xd, L-1, and d was the number of nodes, right? We defined. So each of them are having their own w's, W0 and j, W1j, W2j, WDJ, and all of these w's are representing for the L-1. Then you have to sum them up. That means that you have to calculate their x's with the w's, and then you pass them forward to the current layer. We define S of j So the input in node J and layer L is going to be called S of J of L, which is that. And this represents our node J in the layer L, which is the current layer. And then we apply the activation function, in this case was sigmoid, and then we pass it to the next layer, which was L plus 1, and you have the same thing depending on the type of number of nodes they had. That's why we're going to represent them by the Wj and from 1 up to D from the layer L plus 1. So this is the layer L plus 1. Yeah.
Sorry, can you just repeat why on the left side, like all the W's are WL and then the last one's L minus 1?
Yes. So these are actually minus 1, right? Yeah. Let me see, how did I define it? Oh, actually, since we define it this way, so you see here, the Wi and j of L is weights connecting node I in layer L minus 1, right? So that's why all of them should be WL, actually. So this is wrong. So all of them are L. We define it this way because in order to calculate the value for the node J, we need the layers, we need the input layer of the previous layer. And that's the output of the X's and W's. That's why we make it this way, to make it, a little bit simpler. Because later on we have to do the derivation of those. That's why we set the baseline here. Okay. All right, so let's see how we're going to define it in a vector space. So what's going to be the vector notation of these? So yeah, so base of these, you're going to have x of j of L, which was this, the output of that, as the activation function over the node J. And then Sj of L is as if equal to the weights of the previous layer plus the summation of all weights by the multiplication of x's from the previous layer. So that's going to be like a high level of representation. Let's see here. All right, so in a vector space, we can define our S as a vector of S of L this way. So S1 of L, S2 of L, up to SD of L. So D was the number of nodes. Nodes here. Thus, the output of the activation function theta of S of L was theta of S of S1L up to SD of L, right? Our x's can be represented as the vector of x in layer L as 1, the first one, and the others are the activation function, the output of theta of S of L. So now your W's become the vector of WL as Wij of L for our i's from 0 to D and our j's from 1 to D, right? So let me make sure here. Yeah. So that's the node I in layer L minus 1, and this is node J in layer L, right? And to make it more complicated for you guys, so that's going to be the whole vector. So W, starting from W0 and 1 of L, up towards WD of L, and then you go forward to the last W. WD, L minus 1 of L, and DL, and they are within the R space dimension of D, L minus 1 plus 1, because of your bias, multiplied by D of L layers. So in the back prop, you have to compute the derivation of all of those. Okay. So when we say J's column of WL, it is representing the weight incidence on node J in layer L. So those weight on the layer 8 for the node J, right? In the J's column, actually. Thus, your node S, the vector S of L, can be represented as WL transpose, your inputs of the previous layers, right? So if you expand this, you're going to start from the vector of x0, x1 up to xl minus 1, and then you pass the w's of those x's, w1 to up to l, and then you have the current node, which was the output of the xw's, s1, s2 up to sl. You apply the activation function, and you're going to have the output to the next layer. So this one. Right? So that's going to be the high level process in general. So you can represent it as this. Your layer minus 1, which had the d plus 1 dimension, x's and the w's for that layer, comes to the layer L. We represent them as the node S of L. We apply the activation function, and then we have the x of L, and which is still the dimension of d plus 1. Okay? So I guess I'm going to stop here because, yeah, you wrote so many formulas. So next session, I'll start from forward pass. We define how the forward pass goes. So actually you know it already, but we just formalize it. And later on, you're going to see the backprop. So be ready for that. Okay.